Hey everybody, welcome to Young-Splaining Metabolism. In order to first understand metabolism, you need to understand a little bit about energy. Now, metabolism is the totality of all of your cells' processes, so it's the catabolic and the anabolic processes. And the purpose of metabolism is to transform matter and energy. So, when we're thinking about energy, what's the ultimate source of all energy on this earth? It's the sun. Energy is going to enter our ecosystem as light and then it exits as heat. Now, the laws of thermodynamics tells us there's two laws of thermodynamics, and thermodynamics is simply the study of energy transformations. The first law tells us that energy cannot be created nor destroyed. It can only be transferred or transformed. So the energy that is coming from the sun to this earth is being captured, transformed, transferred until it reaches chemical energy that can be used. And every time this energy is undergoing a transformation, some of it is lost as heat to the universe, which brings us to the second law of thermodynamics, which speaks to those energy transformations, basically stating that every time there is an energy transformation, entropy or disorder of the universe is going to be increased. Now we know that organisms become more organized. The cell takes these macromolecules and these cell organelles and it orders them to become more organized. And cells are organized in the tissues and tissues in the organs and so forth and so on. But as the organism becomes more organized, because there are transformations of energy going on, ultimately the universe becomes more disorganized, more disordered. So there's an increase in entropy. Now, we are systems, and there's two types of systems. There's an open system and there's a closed system. If you think about a closed system, like look at the top right side, top right hand side. This is what we would consider a closed system. There is something in this system, there is potential to do work, but there's no interactions with the surroundings. What's there is there. And as the system seeks to go from an area of instability to stability, as it moves towards equilibrium, what we see is it is doing work. But once it reaches equilibrium, the work stops. So when there's a high availability of energy to do work, we have a high level of instability. And as a system moves towards stability, as it moves towards equilibrium, the ability to do work decreases. Now, organisms are open systems. We interact with our environment. So if you look at the bottom, what you see is an example of an open system. And this is a multi-step open system because that's how our cells process things during metabolism. It does so in a multi-step pathway. Now, in this open system, you see you have something coming into the system, but you also see things are going out of the system. So this system is interacting with its environment. It is taking in from the environment and also putting out into the environment. But if you notice, there's a gradual drop from each level, from one level to the next level. And because of that gradual drop, there's an ability to do more work. And what you notice here is you see delta G is less than 0 in each one of these. And that just means there's a negative change in the energy because every time this energy is transformed, some of that is lost in the form of heat and increasing entropy. Now, if we look ahead to metabolism, it is important to understand that metabolism is talking about the catabolic and the anabolic processes. We often think of it as the catabolic because we think about, my food's breaking down and all of that, how am I metabolizing what I'm eating. But we also need to think about it in terms of anabolic processes as well. Remember, cata breaks, ana builds. So metabolism is going to be all the processes that transform matter and energy. And every chemical reaction between molecules is going to involve some type of bond breaking and bond forming. If I'm breaking bonds, I am releasing energy. And when I am forming bonds, that is an energy consuming process, so it's storing energy. The energy is found in the chemical bonds, not the element itself, but the bonds between those elements, the bonds between those molecules. Now, if I am breaking bonds, that is catabolic because I'm going from something bigger and I'm breaking it down. And if I'm making bonds, that is anabolic. So we have what's known as free energy, and free energy is just the ability to do work when temperature and pressure is uniform, and that's what our cells provide for us, an environment that is uniform as it seeks to maintain homeostasis. So any process that has a positive change in energy, so my reactants, what I start with, has this much energy, and my products have this much energy. How did I get that increase? I had to put energy into that system. And so if I'm putting energy into this system, this is an endergonic or an anabolic reaction. Now, these type of reactions are non-spontaneous. They do not happen spontaneously because they are energy consuming. In this case, we say our change in free energy is positive, or delta G is greater than 0. A system that is at equilibrium, delta G would equal 0, but we know that cells will not come to a true equilibrium. They can have a dynamic equilibrium where the processes are moving in and out. Things are moving in and out of the cell at the same rate, constant rate, but it's not a true, we have stopped moving equilibrium. Now, an exergonic process is going to be one that is catabolic. And catabolic processes do occur spontaneously because they are energy releasing. So my reactants, or what I start with, has this much energy, but then as I break it down, step by step, I'm releasing energy. So my products are going to have less energy, and that is a negative energy change. So they go from high to low. That's a negative energy change. So delta G would be less than 0. So the change in free energy is less than 0. Now, there is a formula that helps you to calculate the change in free energy, and the change in free energy is equal to enthalpy minus the temperature in Kelvin multiplied by entropy. So your change in free energy, what you see here, is delta G. Now, delta H is enthalpy, or that's the total energy of the system, the change in the energy of the system. And you're going to subtract for that temperature in Kelvin. And remember, to get to Kelvin from Celsius, you need to add 273.15 to make sure that you have your degrees in Kelvin, because this calculation needs to be performed in Kelvin, not Celsius. And the last part is entropy, or the disorder. Remember earlier I said that every time energy is transformed, it increases the disorder of the universe. It increases the entropy. And entropy is symbolized with delta S. So let's look at this diagram that is showing an exergonic reaction. So here are my reactants. This is the amount of free energy available in the reactants. Energy is released as this is catabolized, and I'm going to end up with products that have less free energy than my reactants did. So through this catabolic, exergonic, energy releasing spontaneous process, there is a change that is negative. This is a downhill reaction. The negative change makes delta G, the change in free energy, less than 0. An endergonic reaction, one that is energy required, energy consuming, is going to be non-spontaneous. It's going to be anabolic because my reactants are going to require the input of energy as the products are being formed. And so this input of energy causes my products to have more energy than my reactants, and therefore my change in the available free energy is going to be greater than 0. So this is an endergonic, non-spontaneous, anabolic, energy-consuming process. Excuse me. So let's look at an example of that. And how our system overcomes these endergonic reactions and how it uses these exergonic reactions is through energy coupling. So an endergonic reaction is going to be driven by an exergonic reaction. So if I need energy, the energy released by this one is going to force my reaction. It's going to drive that reaction. And their body accomplishes this through the use of ATP, or adenosine triphosphate. ATP is going to be coupled with endergonic reactions. Now, and it does that by releasing energy and also phosphorylating the intermediate. So if we look at the top, we'll see the transformation of glutamic acid to glutamine. Now, this is an anabolic process because in order for glutamic acid to transform to glutamine, it has to combine with ammonia. So I am building this up, right? So I'm adding things together. Bonds are being formed. And in order for the bonds to be formed, energy is required. In fact, this reaction requires 3.4 kilocalories per mole. Now, if coupled with ATP, and the hydrolysis of ATP is going to release a negative 7.3 kilocalories per mole, because remember, energy is released downhill, delta G is negative. When coupled with ATP hydrolysis, when ATP is hydrolyzed, remember you end up with ADP and inorganic phosphate. That phosphate is going to phosphorylate the glutamic acid, creating a phosphorylated intermediate. And the intermediate is just a thing between my reactant and my product. I'm not at my product yet, but this is an intermediate. And so when this happens, I'm going to have my phosphorylated intermediate plus ADP, adenosine diphosphate, and it's what you get when ATP loses a phosphate group. Now the ammonia can be added in, and I end up with glutamine. Now, when I look at this process coupled together, when these processes are coupled, in order to go from glutamic acid to glutamine, I needed plus 3.4 kilocalories per mole. There was a release of negative 7.3 kilocalories per mole when ATP was hydrolyzed. So the net reaction has a negative delta G of 3.9 kilocalories per mole. When you have energy coupling, the overall net reaction of the exergonic driving the endergonic is an exergonic reaction. You must have more energy than you need for energy coupling, because remember, when energy is transformed, some of it is lost in the form of heat. A reaction that gives off 3.4 kilocalories per mole could not drive the formation of glutamine from glutamic acid and ammonia. ATP can be regenerated so ATP goes from ATP to ADP and inorganic phosphate through hydrolysis, and that releases the energy for cellular work. And then the energy for catabolism can be used to drive the force of ADP and inorganic phosphate becoming ATP all over again. So ATP can be regenerated from the ADP and inorganic phosphate available in the cells. So let's look at the organization of a metabolic pathway. Now, whenever you have a metabolic pathway, you're going to begin with a specific organism, and your task is to get to your product. But that doesn't happen in one step. Typically, you're going to have a multi-step process like you saw in that open system. And as an example, I'm going to use the first 3 steps of glycolysis. Glycolysis is a catabolic process that's a part of cellular respiration in our cells. Now, each step is going to be catalyzed by a specific enzyme. The enzymes are not the same in each individual step. What's important to remember is that the product of one reaction is going to be the substrate for the next reaction. So the starting molecule is A. Enzyme 1 is going to catalyze reaction 1, giving me the first product, and that's B. B is the product of reaction 1, but it's also the reactant of reaction 2. And this will continue step by step until you reach your ultimate product. Now, I'm only going to do the first 3 steps of glycolysis. There's actually 10. So this is not the end product, but it's just an example to kind of let you see what's going on. So in this case, my starting molecule is going to be glucose. Uh-oh. PowerPoint's about to shut down. I'll be right back. Sorry. Okay, guys, I'm back. I apologize again. So as I was saying, your starting molecule in this case is going to be glucose. So that's molecule A. Now, glucose is going to be catalyzed by hexokinase, and then that hexokinase is going to, at the expenditure of 1 ATP molecule, glucose becomes glucose 6-phosphate. Now, this is an intermediate. This intermediate is going to be catalyzed by phosphoglucoisomerase. And the phosphoglucoisomerase is going to catalyze the reaction of glucose 6-phosphate to fructose 6-phosphate. This fructose 6-phosphate is now my new starting product. This is another intermediate. The reaction of fructose 6-phosphate is going to be catalyzed by phosphofructokinase. And this is going to, at the expense of one ATP molecule, fructose 6-phosphate, becomes fructose 1,6-bisphosphate. Now this process continues. There's 6 more steps. There's 10 steps in all in glycolysis, but this is just an example of how this reaction would be catalyzed by different enzymes at different steps. Now, enzymes are extremely important because they are catalysts. And a catalyst is simply something that speeds up a metabolic reaction by lowering the energy of activation, that activation energy, those energy barriers. Typically, the activation energy is going to be some thermal energy that's going to be absorbed from the reactants from the environment. But what a catalyst does is it makes the environment correct, or it orients the reactants in a position so that this activation energy is lowered. Now, it does not change delta G. Delta G will be what it will be, but by lowering the activation energy, it makes that uphill climb a little bit shorter so the reaction can happen faster. It's very specific. Enzymes are very, very specific for the substrate. That's the reason why hexokinase catalyzed the glucose reaction, but phosphofructoisomerase catalyzed the glucose 6 reaction, or phosphofructokinase catalyzed the fructose 6 reaction and not the glucose reaction. So enzymes are very specific for their substrate. Enzyme regulation is what controls metabolism. If it was not for enzymes and the ability of enzymes to be regulated, the system would go haywire. Everything will be happening right, left, and so forth. And the way the cell does that is it can either turn on or off the genes for certain enzymes. So if I don't need the enzyme, it's not going to be transcribed and then later translated. For instance, the enzyme lactase breaks down lactose, which is milk sugar. Lactase does not need to be present in the system if there is no lactose. But in the presence of lactose, your body needs lactase to catalyze the breakdown of the lactose or the milk sugar. Enzymes can be altered by pH, by temperature, or by certain chemicals that interact with that enzyme, and that can change the activity of the enzyme. So if you look over to your right, what you see here is just a typical reaction curve. And you have your reactants, and then you have your transition state, which is when the energy of activation is going in. This is when the reactants are absorbing the thermal energy from their environment. And once it reaches a certain point, then the reaction can proceed. Now, what you see below is what happens when an enzyme is present. There is still an energy of activation that needs to occur, but if you notice, that is less. So since it takes less energy to get going, it takes less time to get going, and the reaction can happen faster. Delta G is unaffected. The change in free energy, the change in energy from reactant to product remains the same. It's the time that it takes the reaction to get going because the activation energy is lowered, not the change in free energy that was available. So what you see here is a typical enzyme substrate reaction. You have your substrates, which you see at number 1, and they will attach to the enzyme. They enter the enzyme as what's known as the active site. Now that active site is going to make a change in shape to actually accommodate the substrates. The substrates are going to be held by weak interactions. And while they're being held by these weak interactions, they're going to be converted to products. The products will be released, and the enzyme remains unchanged. Enzymes are not used up, they're not consumed in reactions. The active site is now available for new products. Now that this active site is available for new products, what you will notice is that the active site has what's known as an induced fit. That induced fit brings the chemical groups of the active site into positions that enhance their ability to catalyze the reaction. Now, what I call the active site is the COPS, because the active site lowers the activation energy in one of four ways, and those four ways begin with C, O, P, and S. So the active site, they're the COPS. It can do it by covalently bonding to the substrate. It can do it by orienting the substrates correctly so it gets them in the right position so that the reaction can occur. It can provide a favorable microenvironment, or it can actually strain the substrate bonds. So one of four ways is how the active site actually helps to lower the energy of activation barrier. So I call the active site the COPS. Now, enzymes, again, are affected by temperature and pH. They have an optimal temperature and an optimal pH, and that's the best. They have an optimal range in which they function. Optimal conditions favor the most active shape of the enzyme molecule. And remember, structure dictates function. So when you change the shape of an enzyme, you also change the function of that enzyme. So if you look at the bottom, what you're seeing are two enzyme activity curves. One is showing the temperature and the other one is showing the pH. Now, the highest point of this graph is going to be the optimal range for this enzyme activity. What you see here is it's increasing. It reaches its optimum level, and once you go past that range, that activity begins to decrease. Same thing with the pH. Sometimes enzymes need helpers. Our enzyme helpers are called cofactors. There's two types of enzyme helpers. There are organic and inorganic. An inorganic enzyme helper is simply called a cofactor. All enzyme helpers are cofactors, but if they are organic, we call them coenzymes. And when you think of an organic cofactor or a coenzyme, think of things like vitamins, because they're typically going to be some type of vitamins. If you think of inorganic, think of your ions, like iron ions or calcium ions or sodium ions. Now, I said earlier that metabolism is regulated by enzymes being regulated. Enzymes can be inhibited and they can also be regulated. There's two types of enzyme inhibitors. You have competitive inhibitors and you also have non-competitive inhibitors. Competitive inhibitors are things, it may be a chemical, it may be an antibiotic, but a competitive inhibitor is something that is going to compete with the active site, compete with that substrate for the active site. So it's going to bond to the active site of the enzyme. And if the substrate cannot bond to the active site of the enzyme, then it cannot be turned into the products. So I am inhibiting you by competing with you for that active site. Now, non-competitive inhibitors do not compete with the substrate for the active site. What they do is bind somewhere else on the enzyme. And when they do that, they cause the enzyme to change its shape. And remember, structure dictates function. So if you change the shape, you change the function. By changing the shape of the enzyme, the substrate is no longer able to bind to the active site. So that is an indirect way of inhibiting it, but it's non-competitive. Now, enzymes can be regulated, and that regulation is considered allosteric regulation. And allosteric regulation can inhibit or stimulate an enzyme's activity. So if I look at allosteric regulation, and if you look here at the first one, most allosterically regulated enzymes are made from polypeptide subunits. So amino acids put together. Each enzyme has an active and an inactive form. So in one form it's active, in another form it is inactive. And if it illustrates cooperativity, it can actually be amplified. The enzyme activity can be amplified. So if we look here at the top, we have allosteric inhibitors and activators on part A. Now, if you notice, these are the subunits. See, this enzyme is made up of 4 subunits. So this is what we mean by polypeptide subunits. It's made up of 4 subunits. It's not simply one subunit. There's multiple subunits there. And so the active form is in one way, and the inactive form has the active site shaped a different way. It changes the shape of the actual enzyme. And if you change the shape, you change the function. So what you notice is if the activator binds to this enzyme, it stabilizes it in its active form. But if an inhibitor binds to the enzyme, it stabilizes it in the inactive form. Now, if you look at this, what you're noticing is these can oscillate back and forth between each other. So it can go from active to inactive, active to inactive, active to inactive. And so if an activator binds, it holds it in the active form. But if an inhibitor binds, it holds it in the inactive form. So that's what we mean by allosteric. It can go either way. I can activate or inhibit. Now, with cooperativity, what you'll notice is the enzyme is actually being held in a position that's stabilizing it, and that is increasing the activity of that enzyme. So the last part I want to talk about is feedback inhibition. Now, feedback, think about it. You know what feedback is. If you do something and someone gives you some information on how you did, or if they're telling you, so if you're filling up a bucket of water and you're blind and they're saying, okay, it's not full, you keep going, right? If the goal is to fill the bucket. And once they say it's full, you'll stop. So that's feedback. Or think about a speeding, like one of the things on the road that has like the little, that tells you how fast you're going. Typically, when you see that, if you're going too fast, you slow down. So it's providing you feedback. Now, some people see that and speed up because they want to see if they can break speed laws. Hopefully you're not that person. But feedback inhibition is when the end product in a metabolic pathway can shut down the pathway. So when I get a lot of the product, that product itself can bind to the enzyme. Some of the product can bind to the enzyme allosterically and inhibit the process of that enzyme catalyzing the reaction. So this is feedback inhibition. The product itself is going to provide feedback that alters or halts the production of the product because it's a lot of product there. All right, so that's it for today. Hopefully you understand metabolism a little bit better. Again, I apologize about my PowerPoint. Don't know what's going on. But thank you for listening to Young-Splaining, and this is the first time you actually see my face on here. You may not see it again. We'll see. All right, bye.